A standard internal combustion engine works when a fuel charge is ignited under pressure, pushing a piston down a cylinder where its linear motion is converted via conrod into rotational motion of a heavy crankshaft held in an even heavier block. To increase power, numbers of cylinders are repeated in rows, either inline or in a V configuration, introducing even more weight and complexity. The Duke engine reforms this linear arrangement into a circle, creating a true axial engine. The standard piston cylinder sets are mounted in a single cast and machined monoblock, revolving slowly around and in line with the crankshaft. The pistons drive a star-shaped element called a reciprocator, allowing all moving parts to operate in a purely sinusoidal or wave-like motion. The reciprocator in turn drives a central crankshaft in the opposite direction, a key to many of the Duke engine's advantages. Instead of the usual complicated poppet valve system, the cylinders themselves slide past ports and spark plugs that are mounted in the stationary head ring. As the cylinder slides past the inlet port, the fuel and air charge is let in. The charge is then compressed before the cylinder is exposed to the spark plug. The charge burns, driving the piston down in a power stroke. The piston then rises again, ejecting the combustion gases through the exhaust port to complete the four-stroke cycle. With just 5 cylinders requiring only 3 spark plugs and 3 fuel injectors, the engine has as many power strokes per revolution as a conventional 6-cylinder engine, but with at least a 30% weight saving and an astounding reduction in the number of parts. Originally conceived and developed by Duke founder Noel Duke, Duke Engines has put together an international team to help develop the concept, including experienced engineers previously at Cosworth Technology, now Marla Powertrain in the UK, and other major engineering companies, forming a highly skilled CAD design, analysis and development team. From an initial proof of concept, the Duke team have now developed their 3rd generation design. A rigorous test program conducted at Marla Powertrain has proved the engine's capability and its exciting potential. Even at this prototype stage, key performance characteristics have matched those delivered by conventional production engines. Recent breakthroughs, now the subject of patent applications, pave the way for Duke to approach engine speeds not previously achieved in axial engines. Potential applications of this axial technology go beyond just the Duke engine, opening up further opportunities for this evolving technology. Duke's developing engine technology enjoys a number of fundamental advantages over conventional 4-stroke internal combustion engines. Its compact combustion chamber has no hot exhaust valves present and is remarkably resistant to pre-ignition of the fuel-air mix. It can utilize a higher compression ratio, delivering greater power for a given amount of fuel. Spark ignition Duke engines have run compression ratios as high as 14:1 on 91 octane fuel without detonation, delivering a large improvement in efficiency that leads to lower fuel consumption and hence lower overall greenhouse emissions.